So what Altiscale does is it produces, we provide Hadoop as a service, and we have a variety of personnel from places like Yahoo, Google, LinkedIn, so on and so forth. So for the rest of the talk, we kind of hope to illustrate some of the learnings over the past, as long as Hadoop's been around, what we have learned about managing Hadoop in production deployment. Okay, so you've put together your first major Hadoop deployment. It's running production ETLs. Great, congratulations, okay? We can all go home, right? Well, actually, no, right? First, your production ETL starts running, but then your data scientists say, hey, this is a neat Hadoop cluster, let me get on, and then start building models on this cluster, okay? And then your BI team says, guess what? I really want to run interactive SQL and Hadoop queries on your cluster. So now they get on the cluster, and they start doing their thing. Your mobile team says, why should I be left out, right? So they start sending real-time events into your cluster, and pretty soon, before you know it, you're so successful at this, you're signing up more clients, and the input data for your original use case, your production ETLs, now has doubled. So pretty soon, before you know it, your cluster is like a Lambo stuck in a flock of sheep, right? So it's bogged down, and people are now starting to point fingers at you, okay? So this is what we call the success-disaster scenario. What that means is there is a period of initial success, say your POC or your first production deployment, and then everyone starts piling on the cluster, right? Everyone else, other business units, other groups, and pretty soon your cluster gets bogged down. And then everyone's pointing fingers at you, and there you are. And you have to find ways of getting out of this, okay? So if we had to classify, say, why do clusters fail? So recall I mentioned clusters get bogged down, right? So what does that mean? There could be a whole variety of reasons. So what we're going to do for the purpose of the talk and really, for analysis, right, is really put the reasoning into three broad categories. Quite simply, there would be too much data, too many jobs, or too many users. It could be any one of these, or more likely is not, all three. Okay, so your cluster is bogged down. How do you get out of it? Okay. So the short-term strategy we propose is you try to get resources for your cluster, beg, borrow, and steal for the short term. And the real goal here is to get some immediate headroom, okay, by expanding your cluster size so that you can put into place what we call a longer-term strategy, right? All right. So what exactly is in this longer-term strategy? The longer-term strategy really comes to two major parts. So one is, recall we talked about the failure categories, too many users, too much data, too many jobs. So within each failure category, what we've done is we've identified a couple of real pressure points, right? So this is where the cracks in your cluster first start to appear. These can occur at various levels of the Hadoop stack. So what we want to do is really, this is where the damage really starts to happen first. So if you can see this, it's kind of the canary in the coal mine, if you will. So you can identify and shore up these pressure points. So that's the first part. And the second is really, kind of wringing more capacity from your cluster. Okay, so this talk, we're really going to focus on Hadoop 2. If you're not already in Hadoop 2, you should really consider there's a lot of good things in it. As a refresher course, if we had to look at the stack, so I'm starting from the very bottom level, the machine level, that's the usual operating system, hardware, network, and then there is what we call kind of the core Hadoop layer, which is HDFS and Yarn and all the usual daemons that come part of it, the data node, the name node, for instance, for HDFS, for Yarn, it would be the node managers and the resource manager, right? On top of that is what we call the execution framework, and that is the classic MapReduce, if you will, and then near execution frameworks like Tez and Spark. And that layer is really responsible for the nuts and bolts of implementation. And on top of that is the more user-friendly scripting front end, right? So for Hive and Spark SQL, it would be the SQL portion. For cascading, for instance, it would be the Java, the Java library piece. For Pig, it's Pig Latin, for instance. So on top of this, by and large, is where you'll be building your application. Okay. So let's go on to the first failure category, which is too much data. The pressure points that you'll see by and large tends to be because of HDFS at capacity and because of too many objects. These are by far the most common scenarios when you get to that stage. And they all tend to occur in the HDFS layer. What happens when HDFS is at capacity? You're going to see unpredictable cluster behavior. One of the big reasons is, say, Hadoop daemons can save logs to HDFS, their own logs, and so they start to fail. You're going to see a lot of transient errors, and you're going to see a lot of execution framework errors. For instance, you run a Hive query that tends to produce a lot of intermediate data, and it can't because there is no HDFS to put the data in. So you'll see typical stack traces like what's pasted below that's complaining that there isn't enough, by the way, of replication room for the intermediate files it's trying to produce. The simplest way of mitigating HDFS at capacity is to use HDFS quotas. Here's a sample command that puts in a space quota on a directory. You can set quotas on a per directory basis. Unfortunately, as far as we know, you can't set this per user. It's something we hear a fair amount. It really makes sense to a lot of business units and teams for them to be able to do that, but at this point, it's on a per directory basis. But even then, it is protection against cluster destabilization via, your capacity filling up. The next one is what happens when you get lots and lots and lots of objects in HDFS. So one of my favorite quotes on this is, elephants are afraid of mice, Hadoop is afraid of small files. So below is a diagram that no Hadoop system administrator ever wants to see, and that is the number of directories and files in the cluster, and the number of blocks just below that, and it's constantly going up. This is a cluster of ours, and you can see it's edging at the 12 million mark for the total number of directories and files. Not a good thing. Why this is not a very good thing? Well, first of all, there is memory pressure. The name node heap is proportional to the number of files and directories and objects in HDFS. So if it expands, that puts that much pressure on the name node. The data node is dependent on the number of blocks for that particular node. And so again, if the number of blocks increases, that puts a lot of pressure on data nodes. And out of memory exceptions, data nodes failing is something that we do see when this starts to happen. The other flip side of too many objects is the performance overhead. So typically in MapReduce, for instance, right, there is by default a one-to-one correspondence between, say, a file, right, and the container spawned for it. So if there are too many objects, there's going to be too many containers. And then there's going to be then overhead in spinning up and taking down the containers. And you'll spend a lot more time in the execution framework than at the application layer. So where do you go about finding these objects? We use two ways in order to be able to do this. One is kind of the rough and ready HDFS count. So that's HDFS, DFS minus count. And you kind of start at the top, at the root directory, and work your way down to find where the offending directories are. The other approach is using FS image files. These can be produced by the name node, for instance, and then you run the HDFS OIV command, and it spits out a lot of information on the file system and what objects are where. It produces a lot of information, but the tricky part is you typically have to put together tools and scripts in order to be able to make sense out of what it's putting out. So that's not trivial. So in the short term, what you want to do, again, kind of taking the approach of finding some headroom, is you would increase the name node and the data node heap sizes. And this strategy has limitations. You're limited by the physical configuration of your nodes. And you can increase your cluster node count. That helps with the data nodes, since that means on a per node basis, there are less blocks to worry about for that particular data node. The longer term is, first you find out where the objects are, and then we suggest two ways in which you handle many objects. You coalesce multiple files together into one, so you kind of clump them together, or you use a Hadoop archive. How do you combine multiple files into one? Here's a sample Hadoop streaming job that we have found to be very useful, right? You notice that this is a Hadoop streaming job where the mapper and the reducer are essentially identity type functions. It's cat. So the real fun comes in noticing the mapred.output compress, which is set to true, and the compression codec, which is set to LZO. And you'll also notice that the number of output parts for the file it produces is set to something like 40. It's tweakable, but the idea being that if there are, say, thousands of input files, you're now producing 40, you're producing a single file with 40 parts. And this will work on whatever your Hadoop config is set up to read on the cluster itself. Because it's producing LZO, we'll find that it's useful to build an index for the LZO output. So this is the second part of the process, where you tell Hadoop where the splits are, and you run a command to generate the index for the LZO file that you just produced. So this is useful if you don't really care about, say, the file names. If those don't contain useful information, you simply want to clump all the contents of these input files into one really big file. If, on the other hand, you want to preserve the file input names and the directory structures, you'd use Hadoop archive. So here's the sample command on using Hadoop archive. It's kind of long and clunky, not the most user-friendly, but it does the job, right? So you're going to specify the archive name, the location, the various input directories, all of that good stuff. And what it'll do is, once you issue it, it'll produce a MapReduce job to actually create the archive. One interesting thing we noticed is on Hadoop versions 2.4 and earlier, for some reason, the DFS replication factor for source files, for Hadoop archive at least, is set to 10, which is fine for large clusters, but for small clusters, with nodes, say, less than 10, it's not as good, and it's hard-coded. So in Hadoop 2.6, the powers that be actually added a replication factor that is settable from the command line. So you can adjust that, and that makes life a lot easier, especially for small clusters. And so as I mentioned, these are really useful. Once you produce the Hadoop archive, it's kind of neat. You can actually do LS and all of that good stuff on the archive itself, and it'll tell you what the original directory structure was. All right, so for the next part, I'll hand over to Charles. We'll talk about too many jobs and the for failure category part 2.
Hello. So who in the audience has heard, my job is stuck? My job's not progressing. What's the matter with the cluster? Something must be broken. So this is the class of problems that I'm going to be talking about. Jobs that aren't progressing or don't get started, or the more important job finishes last. So how do we take care of this? How do we solve this problem? First, you need to understand the jobs that are being processed on your cluster. How do we do this? We look at log files, like the resource manager log file, the history server log file. There are some APIs in the resource manager that you can query to see the recent history of jobs as well. What do we want to understand from analyzing these logs? We want to understand the utilization within the queues. We want to understand the utilization of the cluster as a whole, how much time is being spent by containers in a wait state, that is, jobs have been submitted but no active work is being done. We want to look at job level stats. What kind of jobs are going on? I expect this type of job to be running, but really the bulk of my cluster's capacity is being used by this type of job or this user. And then we'll use techniques to make sure that the cluster is behaving, queue tuning techniques to make sure the cluster is behaving in the way we want it to. So what type of information is available in the resource manager log? This will talk about jobs and containers. It tells you what queue a job is run in, job stats like when the job started, stopped, how many containers, each individual container, when it was started, when it was stopped, how much resource in terms of memory and CPU was allocated to it, did it fail, did it succeed? And then if you're running MapReduce jobs, there's the MapReduce job history files, which go a little bit further, talk about things like how many bytes, how many files did it read from HDFS, how many did it write, how much CPU time was spent on map, how much was on reduce, how much CPU time was spent in GC, what was the maximum number of parallel reducers and mappers. Again, this is MapReduce job history server. It's not available for Tez and Spark. There is a timeline server, which is a generic application history server that applications can produce information for. But the MapReduce job history server is MapReduce specific. So analyzing logs, what are you saying? Yes, it's hard. It's writing custom scripts to parse the job information, the container information from logs that you're interested in. In every place I've been involved, this turns into a data pipeline of its own, right? We process all the job logs, put it in a data warehouse, use BI tools to visualize it. There's not really a strong set of open source tools for visualizing or analyzing cluster usage at this time. So a lot of it is custom. If you take many, many hundreds of man hours and work really hard at it, you get simple things like this. The top graph here is like container wait time. This is over the course of a day, probably a few hours. So the big green spikes are how many seconds each container had to wait between the time it was requested and the time it actually started performing work. The middle graph is queue utilization in terms of memory requested and memory available. The bottom graph is the queue utilization in terms of vCores requested and available. The different colors are different queues. So for instance, the second big spike in the container wait time graph, you'll notice that there's both a large job in the production queue and a significant job in the interactive queue, and both of these are waiting on containers. While the production queue is constrained to 80% of the memory, it's still waiting. Another way to look at this type of data is I built my cluster to do this job. Is it doing this job? One of the ways you do that is you look at the types of jobs that are running. So we've broken down the jobs by count into what type of jobs they are. So there's no JHIST. That means there's no job history file, which means it's not a MapReduce job. And for a bunch of different common types of MapReduce jobs that we saw in this cluster, we've broken them out. Camus, DistCP, Hive, Pig, Squoop. And then we also have this other, which is a MapReduce job that's not one of those categories. So you can kind of see this is a daily graph, and sometime towards the end of the month, somebody started playing with Squoop, right? And they were probably moving a lot of data during the first 19 days of the month because there's always, one or two DistCP jobs running per day. Another way to look at this data is the breakdown by user, right? I built this cluster for this purpose. I expect these people to do ad hoc jobs. I expect a pipeline to be always running. So for instance, if you look at the orange bars in particular, I'm guessing this is a real person because there's 5 days of jobs and 2 days there aren't jobs, and then 5 days that there are jobs, and then 2 days there aren't jobs. So he probably doesn't work much on the weekends. It looks like he had a doctor's appointment on Wednesday of that last week because there's no orange bar there. But you can kind of get a deeper understanding of who's using your cluster and when, right? So someone's complaining that his job isn't starting. Well, I see that he only ran it on the 19th, and there were tons of jobs run by other customers at that time. Maybe I suggest he does his processing closer to the 9th when the cluster is less lightly utilized, or more lightly utilized. So, all right, we got all this data. We kind of understand what's going on now. People are still complaining. Okay, what do we do about it? First, decide how you want your cluster to behave, right? I need my production jobs to get this amount of resources all the time. I need data scientists performing interactive research to use whatever portion of the cluster is available at any time. So here's some real-world examples that we've seen. Data loading jobs constrain it to a very small queue so that the bandwidth used by those is constrained. Or in some cases, business unit A funded 60% of the cluster and business unit B funded 40%. So that's how we want the resources allocated. So bottom line is pick the strategy, decide on the direction you're going. And then use one of the modular schedules of Hadoop to implement that strategy. The two schedulers that are distributed by default are the fair scheduler and capacity scheduler. The resource allocation for the fair share is such that the jobs get an approximately equal share of resources over time. The capacity scheduler is queues are allocated as a fraction of the percentage of the cluster. They both manage memory and optionally CPU reservation. Inter-queue constraints, so the way that queues are divvied up with the fair share scheduler, the max and minimum shares of the capacity are defined, whereas with the capacity scheduler, the minimum capacity is defined as a fraction, some percentage of the entire cluster, and then the maximum capacity of each queue can be larger. The sum of the maximums can be larger. In terms of intra-queue, when you have two jobs in the same queue conflicting for resources, the fair share has the FIFO, the fair, and the dominant resource fairness options, whereas with the capacity scheduler, you basically can control, for the first X users, each gets an equitable 1 over X fraction of the cluster. And then if you have one user that submits a bunch of jobs to the queue and nobody else, then it's effectively FIFO for that one user. There are lots and lots of knobs on both of these schedulers. Can't do it justice as part of a talk. So you really need to understand the scheduler you're using in order to make the cluster behave in the way that you want. I suggest looking at the talk in 2009 by Matei about the fair share scheduler, and later today, Sumit Singh and Nathan Roberts from Yahoo will talk about some of the capabilities of the capacity scheduler. Another type of issue we see with my job isn't running fast enough is when you're running a cluster that has mixed workload. So these three objects at the top represent different queues, and the size of the circles represent the amount of resource required by that job. So imagine, for example, in Q1, you have a very large Hive job. Hive job is typically composed of, 1.5 gigabyte mappers, 2.5 gigabyte reducers, and there's lots of them, right? And Q2, think of it maybe as a Spark job that needs 6 very, very large containers, and Q3 maybe an H2O job that needs 8 very, very large containers. So the interaction in these Hadoop schedulers is, for instance, if the Hive job was there first, it's going to put a bunch of tasks, a bunch of containers on each of the nodes and consume, just a little chunk of each, and it's going to spread them out over there. And then if you submit the Spark job next, you have to, if the container size is basically the amount of resource available for that node manager, it's only going to be scheduled once. And it has to wait until the Hive job has vacated the capacity of that scheduler to consume it. So in this situation, you've got these 3 jobs running, but because Spark and H2O each require that all of the containers be running to do any useful work, they're not doing any useful work. But the Hive job, since it's MapReduce, is progressing. So this could give the appearance that my job is stuck or my job won't start. So a couple of guidelines: run the smallest container necessary to do your work. That will help with the overall throughput of your cluster, and it'll reduce the probability of this type of issue happening. There is some work in the community with node labels and gang scheduling to allow jobs to be more precise about their scheduling needs. And David Chaikin, the CTO of AltaScale, will be giving a talk later today at 2:35 about our experience in this area, in particular with Spark and MapReduce. So one thing you should understand is that configuration at all levels, the cluster configuration, make sure that you don't do silly things like set your MapReduce Java ops to 2.5 gigs while setting your MapReduce map memory to 1.5 gigs, right? You pass in to the actual JVM that gets launched XMX 2.5, but you only allocate 1.5 gigs container. So boom, things blow up. The typical Linux kernel configuration, right, the out of the box, is not appropriate for Hadoop workloads. So you need to do some investigation, take time to make sure that your kernel configuration is correct for Hadoop. You need to do things like use the Linux container executor and enable Hadoop security to ensure that you allocate the resources of your cluster in the way that you intend. Another thing, when you're like running Impala on the same node that you're running node manager on, Impala is not controlled by the resource manager, so you must make sure that it stays in its box. So use tools like cgroups to put limits on other processes running on the box, as well as the Hadoop processes themselves. There are still limits on what Hadoop can control, right? Cgroups, Hadoop's implementation of cgroups controls CPU. It doesn't control memory. The traditional memory management is used, and it doesn't even attempt yet to control network and disk bandwidth. So you need to be aware of all these facts. So another failure category is too many users. The success disaster scenario, you've got different groups of people with different agendas and different needs all running on the same cluster. So we need to make sure that the cluster enforces data access control and resource allocation the way we want it to. So in terms of queue access, Hadoop has the ability to allow you to specify groups or list of groups or list of users that have access to both submit and administer jobs in a queue. So make sure you set those so that data scientist says, well, that queue named production isn't being used right now. I'll submit my job into it. And in addition, if you have different business units that are wary of seeing each other's jobs, you can also restrict who can view what. By default, Hadoop does support Unix-style file permissions, not POSIX semantics, but Unix-style file permissions. However, it's easy to circumvent. You set an environmental variable, tell it you're the super user, and it says, okay, you're the super user. So use Kerberos. Use Kerberos. This is how you prevent this from happening. Say I hadn't done that yet, or even if I did, I want to know who deleted this file at a particular time. HDFS and Resource Manager as well have the ability to enable audit logs, which allow precise tracking of who did what when. And of course, it was Soam that deleted my file because that's what he does. How do I squeeze more capacity from my cluster? There's no magic bullet. The areas I'll focus on are the core layer, the execution framework, and the application layer. So that is interesting. And I have no control. All right, I guess I'll try to remember the slide. So the three areas that I was talking about are the application, the execution framework, and the core. So the optimization of your jobs, right? If you're using Hive, is it the optimal SQL for this query? If I'm writing MapReduce jobs, am I using the right algorithm? Is there a more efficient algorithm? These, while they, just like in RDBMS's, the tuning of the SQL query is a significant improvement. These are the hard part, right? These are the custom queries that take developers lots and lots of time. The Hadoop core itself is over time, it improves performance slightly, but the real bang for your buck right now is in keeping your execution frameworks up to date. Over the last 2 years, Hive and Tez, the Stinger project, and Spark have both shown huge improvements in performance. So the biggest bang for your buck in performance and squeezing more out of your cluster is going to be updating your execution framework.
They're also a lot easier to update than say Hadoop is, right?
Yeah. Sometimes it's just jars in a path on the HDFS. That was, fortunately, near the end of our slides. You didn't get to see the last slide, but that was it. At this time, we can answer any questions you might have. I'll answer that one. I stick my head into that lion's mouth all the time. So there are, sure. Is it a good idea to have separate clusters for test and staging? Test and production, right? Is that a good idea? Did I accurately relay your question? Yes and no. So for AltScale is a platform as a service. So for our customers, we encourage them not to. We encourage them to have a test queue and production queues and have access control lists on each of those queues such that people who are developing their applications submit into this queue and are constrained to this portion of the resource, and production jobs get this much of the resource. So that's talking about the development of the applications themselves, right? I'm developing version 2 of the application on the same platform. In the event that you're testing a new version of Tez or a new version of the Hadoop core, sometimes it's useful, right? If you're worried, right? If you look at the release notes and see, okay, well, that intersects with some feature that I'm using, or I want to turn this new feature on and not destabilize my production cluster. A lot of times the only recourse you have is to spin up a separate cluster. Is this work published anywhere where we can get at it? I
Yeah, I mean, I'm sure it'll be made available as part of the Hadoop Summit slides, and
Right.
we'll also probably put it up on the AltaScale SlideShare. Not probably, we will put it up.
We will put it up.
Yeah, sure.
What's your question? All right, I'll restate the question. Give me a yell if I get it wrong. When I talked about the different sizes of the containers running, is there any way to say, okay, I allocated X gigs of RAM, but it only used Y gigs of RAM, which is smaller? Are there any metrics to see that so I can know when it's appropriate to turn down my container size? Is that correct? I don't know of any. Do you know of any?
Well, I mean, the resource manager logs will tell you the amount of memory it allocated to the container, right? So even if you say from the command line that I'm allocating, for a MapReduce job, say 3 gigs, the container may not get 3 gigs right away, right? It's going to keep on, the resource manager will keep tweaking it up and down. So that's what the resource manager allocates. Now, how much is actually used by the process is not really, I mean, it's somewhat tracked by Hadoop, right? It's tracked by the node managers and ptrace and whatnot.
If you turn up debug level,
Yeah.
The ptree output will be shown, but I don't suggest that on a production cluster.
So yes, there is that gap between like what's allocated, even at a finer level, right? And what's actually used.
They had a question here and then one more back there. So the question was, some types of failures are caused by the application that a user might use in that it's faulty. Another type would be the application that a user is running in that it uses a significant amount of resource and causes pressure on the system. And how can you tell between these two types? And what's the percentage from our observation? I don't have any data on that.
Yeah, I mean, it's purely anecdotal, right? I mean, there are
As many as there are users in the world.
Yeah, I mean, we actually cut out a section because of lack of time on what we call kind of runaway processes,
Yeah.
right? That would have addressed
Yeah.
items like users essentially running jobs that act as internal denial of service attacks because they open up so many connections.
Yeah. A quick question in the back, hopefully. Yeah, that's a tricky one. Different types of workloads on the same cluster. Again, it's determine the behavior you want, right? I want interactive SQL to be able to balloon up, but only to unused resources and get a minimum amount of this. So I think the important thing is to decide what you want and then look at the scheduler capabilities to try to implement that for you. It's it's a hard thing to do and takes iterations on log analysis and tuning. Well, we are actually over time, so thank you very much for coming to see us today.